Engineers did something insane to build the Burj Khalifa. They pushed concrete 700 meters straight up from a pumping station on the ground through steel pipe. And that should have gone terribly wrong, because concrete weighs about 2.5 tons per cubic meter. At full height, more than 26 tons of it sat inside the pipeline at once, pressing back down toward the pump. Dubai's heat was already trying to make the mix harden. Friction increased with every meter, and the journey to the top could take around 40 minutes. If the flow stopped for too long, the concrete could turn into a solid plug trapped deep inside the world's tallest building. So how did engineers push something this heavy that high without the pipe bursting, the pump failing, or the concrete hardening before it reached the top? Well, first they had no practical choice. The Burj Khalifa needed concrete almost non-stop for its central core. 3 wings, columns, walls, and floor slabs. Crews could have lifted it in buckets using tower cranes, but at this height, that would have been painfully slow. Every bucket would need to travel hundreds of meters upward, unload, return to the ground, and start again. And those cranes were already busy lifting steel, formwork, machinery, and construction materials. So pumping the concrete through a pipe saved huge amounts of crane time. Now, the concrete didn't actually go all the way to the tower's 828-meter tip. The reinforced concrete structure reached about 586 meters, but crews pumped concrete as high as roughly 606 meters during one operation. Above that, structural steel continued toward the top. The main core walls used concrete rated up to 80 MPa. Other upper sections used 60 MPa concrete, while the floor slabs used around 50 MPa. So the pump had to move some of the strongest concrete used in the project higher than any skyscraper had managed before. And a normal concrete pump was never going to survive that job. So Putzmeister built a special pumping system for the tower. At ground level, 3 stationary pumps sat beside the building. 2 were super high-pressure BSA 14,000 SHPD pumps. The third was a BSA 14,000 HPD. The 2 larger machines could theoretically create more than 400 bar of concrete pressure. That's roughly 400 times normal atmospheric pressure. But on site, crews limited them to around 250 bar to keep the system under control. Each high-pressure pump used a 470 kilowatt Caterpillar diesel engine. The pumping station also sat around 70 meters away from the tower's center. So before the concrete even started climbing, the pump first had to push it horizontally across the site. Then the pipeline turned upward and disappeared into the building. Ready-mix trucks poured each batch into a large hopper. An agitator inside kept the mix moving and guided it toward 2 powerful pumping cylinders. One piston pulled backward and sucked concrete into its cylinder. At the same time, the second piston pushed forward, forcing concrete into the delivery pipe. Then an S-shaped transfer tube swung across and connected the pipe to the other cylinder. The pistons switched jobs. One filled, the other pushed. Then they switched again. This rapid back-and-forth cycle kept the concrete moving upward in powerful pulses. But each stroke wasn't only pushing the concrete inside one cylinder. It had to move the entire column already packed inside the pipeline. At the record height, that line held around 11 cubic meters of concrete, more than 26 tons. And all of that concrete had to travel through what was basically a steel artery running up the tower. For most of the climb, the Burj Khalifa used high-pressure pipes about 150 millimeters wide. Separate lines carried concrete toward the 3 wings and the central core, so crews could feed different parts of the structure without relying on one single pipe. A 150 millimeter line has around 44% more space inside than a 125 millimeter one, and that extra room cut the pumping pressure by roughly 25%. Near the highest floors, engineers switched to smaller 125 millimeter pipes because crews could handle and reposition them more easily. Then, at the active construction level, the pipe connected to massive placing booms. The 3 wings used booms reaching around 28 meters. The central core used an even larger one, with a reach of about 32 meters. These booms attached to the Doka self-climbing formwork. So as the building grew, the formwork and placing booms climbed with it. But even the strongest pump in the world couldn't push normal concrete that high. The concrete itself had to be redesigned. Inside the pipe, the mix moved almost like one solid plug. The larger particles stayed toward the center, while a thin layer of cement paste and very fine material formed against the steel wall. That slippery layer acted like lubricant, helping the main mass slide upward with less friction. To create it, engineers made roughly half of the aggregate in the tower mix as fine material. They also added fly ash, silica fume, and powerful chemical superplasticizers. These additives made the concrete flow more easily without crews simply pouring in extra water, which would have weakened it. Even the size of the stones mattered. When engineers reduced the largest aggregate from 20 millimeters to 14, the pressure needed to move the mix dropped noticeably. Some mixes used particles as small as 10 millimeters, so the concrete had to behave in two completely different ways. Inside the pipe, it needed to flow smoothly for hundreds of meters, but once it reached the top, it still had to harden into concrete strong enough to hold up the tallest tower on Earth. And before engineers trusted that mix inside the real building, they tested the entire journey on the ground. Near the site, crews laid out around 600 meters of high-pressure steel pipe. The pipe measured 125 millimeters across, almost the same distance the concrete would later travel upward. Pressure sensors sat at 250 meters, 450 meters, and at the very end of the line. Then crews pumped 5 different concrete mixes through it. They watched how much pressure each mix needed, how quickly it lost its ability to flow, how much heat it picked up, and how different stone sizes changed the friction inside the pipe. The results showed that slump flow dropped by about 27 millimeters for every 100 meters traveled. The concrete temperature also rose by around 1.2 degrees Celsius over the same distance. And the tests didn't go perfectly. One blockage happened after a delay gave the concrete enough time to start setting inside the line. Another happened when crews combined 2 chemical admixtures that didn't work together. But those failures were exactly why the test existed. It was much better to block a pipe lying on the ground than one buried hundreds of meters inside the Burj Khalifa. And once the real pumping started, Dubai's heat made that danger even worse. Daytime temperatures in the shade could climb beyond 50 degrees Celsius. At that temperature, the concrete could lose workability fast. If it became too stiff during the climb, the whole pipeline could lock up. So crews carried out major pours at night. They also kept the concrete below about 33 degrees Celsius when placing it. And during the hottest months, they replaced nearly all the water in the mix with flake ice. That cooled the concrete before it even entered the pump. At the highest levels, one batch could take around 40 minutes to travel from the hopper on the ground to the outlet above, and crews wanted it inside the pipeline no later than about 90 minutes after mixing. But even before the first batch entered the pipe, crews had to prepare the line. They pumped a thin lubricating slurry through the steel first. That slurry coated the inside of the pipe and helped the concrete slide in without catching against the dry metal. But even this step could go wrong. If the slurry contained too much water, it could break apart the concrete mix behind it. The line also had to stay completely full. If air slipped inside and became trapped under that massive concrete column, the pressure could compress it like a spring. And when that air finally escaped, it could make the heavy delivery hose whip around with explosive force. So crews watched everything: pump pressure, concrete temperature, flow rate, the amount of concrete left in the hopper, and exactly how long each batch had been traveling. And that's what made this system so impressive. Pumping concrete into a super tall tower wasn't simply about building the strongest machine. The pump had to match the pipe had to match the concrete, and the concrete had to survive hundreds of meters of pressure, friction, heat, and travel time without setting too early. From the ground, it looked like concrete entered one pipe and somehow appeared in the sky. But inside the Burj Khalifa, engineers were controlling a 26-ton moving column that could turn solid at any moment. And that's just one of the hidden engineering systems that made the world's tallest building possible. If you're all about mega projects, extreme construction, and the insane hidden stuff inside the world's tallest buildings, make sure to smash that subscribe button and go watch the previous videos. You're not going to want to miss those. I'll see you there.